All right, hello AP Physics fans. Today we're getting two more equations, and that'll be the last two equations for this unit. If we take the three equations that we've been given so far and mush them together, we can get a super equation, which looks like that. This is me doing that for you just to show you where it comes from. But I promise you, if you combine those three equations properly together, you do get this equation. Um, so it's the displacement is equal to the initial velocity times time plus the acceleration times time squared over 2. Now on your AP equation sheet, it looks like this. So they've got x and x naught. Well, if you subtract x naught off on both sides, you get x minus x naught, which is delta x. So to me, I think it's just easier to keep it in terms of delta x, but usually your x naught is going to be 0, so this is going to go away anyway. And that's your initial x velocity, and this is just saying this is 1/2 your acceleration in the x direction times time squared. So this would be a big equation for us. This is an important one. So what would acceleration would cause a car from a dead stop at a position of 240 meters to end up at 110 meters in 30 seconds? Well, let's take a look at what we're given. We're starting from a dead stop, which tells me that my velocity, my initial velocity is 0. We're looking for the acceleration, so A is my question mark. We're given the initial position x1 is 240, and the final position is x2 is 110, and we're given time. So what we need to do is we need to calculate the displacement, which is x2 minus x1, which is going to give us 110 minus 240, which is going to give us minus 130. And then plug the numbers into this equation, which I do here. And again, I'm not going to spend much time going through the calculations. I figure you can pause it and review these if you so desire. So this is the last big equation for this unit. V2 squared equals V1 squared plus 2a delta x. And the big variable that's left out here is time. Time is not mentioned in this equation. So if you're missing time and you're not given time in the problem, this is probably the equation you want to look at. So it's important to note that these two velocities are squared, okay, and then this component is not squared. This is what it looks like in your equation sheet down here. Vx, so this is your final x velocity, this is your initial x velocity, equals 2a times delta x. So this is what it looks like. Hopefully it's not a big deal going back and forth between these. I prefer this format. So working a problem with this, a car accelerates at a constant rate of 2.5 meters per second squared, finishes an 810 meter long track with a final velocity of 64 meters per second. What was its initial velocity? So we're given A equals 2.5 meters per second squared. We're given displacement equals 810. That's 810, excuse me. The final velocity, V2, equals 64 meters per second. What was its initial velocity? So that's our question mark. So at that point, you just substitute in into here, and I work this problem on the next slide right here. So this is how you would work that, and we're going to move on. So these are your equations that you're going to be using this unit, and you'll use these in further units too. So don't think that you just can just let these go slide after this unit. But you know, there's not much that I'm expecting you to memorize. You just need to know how to use them. One thing to keep a note of is that units need to match, which basically means that displacement needs to be in meters, the velocities need to be in meters per second, and the acceleration needs to be in meters per second squared, and time needs to be in seconds. So if those all match, then you're in good shape. Okay, So I do work these, but on the next slide. But I'm just gonna do what I was doing before, is just kind of introduce the problem and then show you the slide on how it's worked and move on. So a person drops a ruler from rest and accelerates at 9.8 meters per second squared. The ruler is caught after traveling 15.3 centimeters. How long did it take the person to catch it? Well, the first thing we know is that the gravity is accelerating. The acceleration is 9.8 meters per second squared. Now here I made it negative. Why did I make it negative? Because it's downward. So we're going to consider down to be the negative direction and up to be positive. The displacement is minus 15.3 centimeters. Okay, also negative because the displacement is down. Now, if you had made these both positive, and if you had called down positive, you would have ended up without making a mistake on this particular problem, because we could have called down positive and no one would have been the wiser. But I'm just showing you with the negatives. Now, remember what I just told you about units. Units need to match. So this is in centimeters, so we need to convert that into meters, which I'm sure you remember how to do. Move the decimal place twice, okay, and you got centimeters. And so we're looking for time. What equation is going to help us? Well, there's one thing that we forgot to write down. What do we know about the ruler that we didn't write down? That is that the ruler started from rest, which is our v1 equals 0. I'll give you a hint. Whenever your initial velocity equals 0, that makes this equation pretty easy to use, because this component right here, this v1t, goes away. So that's probably going to be the equation that we use, and it is. And this is how we solve that here. A car has initial velocity of negative 35 meters per second, so v1, whoops. Oh, it's because I didn't turn the drawing on. Let's see. So v1 equals minus 35 meters per second. Okay. The acceleration is equal to 6.5 meters per second squared. We're given time is equal to 23 seconds. Boy, this drawing tool really does not work as well as I'd anticipated. And the displacement is what we're looking for. So delta x, it doesn't equal 0, equals question mark. That does not work that well. Oh well. So what equation do we want to use for that one? Well, we can go and use the same equation here. We're going to find the displacement. We've got v1, t, a, and t. So plugging it in like so, we get our answer. Now, there's another way we could have solved that. We could have used all three of our equations. We could have used these three guys and solved it that way. But why take 3 steps when we can do it in just 1 step? That's what I say. Okay. What is the final speed of a meteorite which enters our atmosphere at? I don't know how long I wasn't recording for, so I'm going to assume that we were probably recording this last problem. Okay. So how long will it take to travel 524 meters with an average velocity of 12.4 meters per second? So t is our question mark. The 524, that is our displacement, 524, and the average velocity is 12.4. So which velocity is that? V1, V2, or V bar? That is V bar. V bar equals 12.4 meters per second. So what equation would we use for that? We just use this one. We would just use this first equation, and I don't think I actually worked that one out because that one's pretty basic. Just to remind you, you can still use the old equations from before. A car starts from rest and accelerates to 15.6 meters per second in 61 seconds. How far did the car travel in this time? Okay, so let's mark what we know and what we're trying to. So v1 equals 0. Don't forget about that one. v1 equals 0. Now I can't read this. V2 equals 15.6, and t equals 61 seconds, and we're looking for delta x. So we've got v1 v2 t, and we're looking for delta x. So the equation that we're going to use is we can use the average velocity to figure out its average. Well, we can use this to find the average velocity, and then I think I worked that over here. Yeah, here's me working it right here. Okay. This equation is a little bit quirky, so I just wanted to say a couple things about it. It's based on conservation of energy, and energy itself is not a vector. So we lose some directionality in our equation, and we'll show you what I mean. So basically, the equation, the signs that make that for V1 and V2 don't end up mattering when you put them into the equation. The signs don't end up mattering. And when you get an answer for V1 or V2, it doesn't necessarily include the correct sign that you want. These signs do matter. So the sign on the acceleration is important, and the sign on the displacement is important. And if these signs are the same, then the velocity is going to increase, and if these signs are opposite, the velocity is going to decrease. So this is the component that tells you whether or not you're going to speed up or slow down. So, but as far as the actual direction of the velocity, if you pull out a velocity direction, which way it's going, you kind of have to think a little bit through. For example, this problem, we've got a car, and it's initially stationary, and it accelerates forward at 1 meter per second squared. What is its velocity when it's 4.5 meters ahead? So whenever we're looking for the velocity on this, we want to just sanity check the sign on it to make sure it's in the right direction. Well, if it starts from rest and accelerates forward, the sign on its final velocity is going to be positive. So it's got to be greater and positive. Here we've got a car, and it's initially moving forward at 7 meters per second. It accelerates backwards at -1 meters per second squared. What is the velocity when it is 6.5 meters behind where it started? Well, if we're looking at it, the direction of the velocity of it when it was behind when it started, it has to be moving to the left. I mean, our velocity has to end up negative. So if we'd gotten a positive answer for that, we would have probably needed to sanity check that and go, oh, okay, it's actually going to be a negative velocity. So here we've got a car. It's initially moving forward at 5 meters per second, and it accelerates backwards at 1 meter per second. What's the velocity when it's 4.5 meters ahead of where it started? Well, if we look for the velocity here, well, think about it. Okay, there's actually two answers for that. There's a positive velocity and a negative velocity because it was moving forward on the way through, okay, and then moving backwards on the way back. So when we look at our answer, when we solve this, we're going to get that our V2 squared is equal to 16. So our V2 could have been positive or negative forward, depending on which point we were looking at it at. Okay, and that's it for this. Now you can do up to worksheet or up through worksheet 2.6, and good luck.